Welcome to the first video in Unit 5, where we'll be taking what you've learned from Unit 4 about carbonyl function and structure and applying it to some specific kinds of reactions, and in particular a class of reactions that involve substitution at an acyl center. To motivate what I mean by this, we could look at this explosion chart. We've got a carboxylic acid here, and it looks like we can make acid chlorides from that carboxylic acid. The same thing would be true of esters. Esters can be made from carboxylic acid, so can anhydrides, so can amides, and so can thioesters. Or in other words, just like we alluded to earlier, all of these different functional groups are on the outside of this diagram, all derive, at least in principle, from a carboxylic acid. That's what we call these carboxylic acid derivatives. And if we look carefully at this set of reactions, these 5 different hypothetical processes, we find something kind of interesting. It looks like part of the structure stays exactly the same. In all cases, I'm retaining my R group and the carbonyl, but what's changing is what's attached to the carbonyl, and as I've drawn the structures on the right-hand side. So we're losing this OH group and we're gaining a chlorine, or we're losing the OH group and we're gaining an OR prime group. So this could be like methoxy or ethoxy, for instance. We're losing an OH group, we're gaining this unit here with another carbonyl, then our anhydride, or a nitrogen and an amide, or a sulfur and a thioester. So when we're seeing this, where it looks like we're removing one part of a molecule and then directly replacing it with some other group, like a chlorine, we call these substitutions. So all of these reactions are quote-unquote substitutions. And you've seen these kinds of reactions before. When you learned about SN1 or SN2 reactions, you learned that a leaving group leaves the molecule and a nucleophile directly takes its place and nothing else in the structure changes. That's what we're seeing here. But we can also focus on a specific place where it's happening. It looks like this part of the molecule, the R group and the carbonyl, those seem to be staying the same. And in particular, we can focus on this bond between the carbonyl carbon and the oxygen, for instance, of our carboxylic acid. That bond seems to be changing. We don't know exactly how yet. We don't know the mechanism of these kinds of reactions, but it seems to be the case that the CO bond is going away somehow. So what we could say is that this piece here, we're going to call this an acyl, group ACYL. Please don't pronounce it acyl, as funny as that might be. And what we're doing is substitution at the carbonyl carbon of the acyl group. So we could say these reactions are substitutions at carbonyl C of acyl center or group. So just like we talked about SN1, each of those letters corresponds to some important information. The S stands for substitution, the N stands for a nucleophile being involved, and the 1 tells us something about the reaction kinetics, that it's unimolecular. We call these reactions SNAc processes. So S for substitution. As we'll see, there's going to be a nucleophile involved, N, and then we're doing this at an acyl center, AC. So when you see the kind of abbreviation or acronym SNAc or SNAc, what we're describing is a reaction that follows this pattern, that we're replacing something that's attached to a carbonyl carbon with something else. So we could say here that this unit is really about SNAc reactions. So just to anchor this a little bit more deeply in what you already know about substitution reactions, and by analogy to SN1 and SN2, you realize that there needs to be a nucleophile, which we haven't yet talked about, but there also needs to be a leaving group in all of those cases. And if we look at the structure that we're starting with here, it must be that this OH group would be our so-called leaving group, or LG. So the incoming nucleophile must correspond to the other pieces that you see here. So for instance, if we were going to run this reaction to make the acid chloride, for instance, you might expect that we would need Cl- as a nucleophile. The same thing might be true for this situation. You might need this oxygen and the R group as a nucleophile, for instance. And you could keep going around the explosion chart, filling in what you would expect to see nucleophiles. So, at least at first, this reaction looks a lot like an SN1 or an SN2. We're replacing a leaving group with a nucleophile. So we could say that there's some similarities SN1, SN2, but there's also some important differences, which we'll actually focus on in some level over the course of this unit. We could also look at a general SNAc reaction, so rather than having specific functional groups like carboxylic acids or a chlorine as a nucleophile, we could do this in the most general way possible. This will actually be helpful for us, because having a general notion of how these reactions look makes it easier to know all of the permutations that are possible that are all SNAc reactions. Memorizing each of these would be a pain in the butt. I strongly recommend you do not try to do that. Rather, get good at identifying the parts of structures that have particular roles, as for instance, like a compound that could be a nucleophile, and then you can slot it into knowing one thing, this general form for a SNAc reaction, rather than knowing a bunch of specific things. So if we look at our structure here, we've got something that we'll label as a nucleophile, something generic. Maybe it's an OH minus or an S minus of some kind. Doesn't really matter. The point is that we have a nucleophile. We've also got our compound that has the acyl group. So that would be my R and my carbonyl, and what I'm going to call a Y group. So this could be anything. It could have been the OH group from a carboxylic acid. It could be a chlorine from an acid chloride. But the point is that this Y group will behave as a leaving group. So this will be our Lg. And what we know is true about SNAc reactions is that the nucleophile will directly displace the Y group and leave the carbonyl and the Y and the R group seemingly intact. We don't know mechanistically what's happening yet. We'll talk about that later. But we do know that the nucleophile will take the spot of the leaving group. We have to be careful, though. The Y group doesn't just disappear. It's going to actually depart with a pair of electrons that were in this carbon Y bond. So the other product we'll have is the anion of Y, whatever it is. These reactions are actually reversible. Because if we look at our products, we have the possibility that maybe Y minus, maybe that's a good nucleophile. In which case, maybe it could displace the nucleophile that came in. That's a possibility, and we'll actually find a lot of examples where that happens. So our leaving group could be a nucleophile in a reverse reaction. We don't know yet. We'll talk more in this unit about how we could make some predictions about whether the reaction will be favorable, in which case products will be formed over reactants, or unfavorable, in which case we would basically run the reaction mostly backwards, and we'd have mostly reactants at the end of the process. So let's look at some specific examples of SNAc reactions so that you can see how we could map these generic ideas onto real compounds. So we'll start with an acid chloride. It looks like this. I'm going to try to make sure that I draw all my lone pairs in for the Y group in particular, because we'll find that that becomes important for us. And let's use methane thiolate, so S minus, as a nucleophile. So I've got to make a few decisions here. I need to decide which structure is likely going to be the electrophile and which structure is likely going to be the nucleophile. We know that unstabilized electrons tend to be sites of nucleophilicity. So in other words, what I'm looking for is like the place where there's the least stabilized set of electrons in the molecule. If I look at all of my lone pairs, so I'll include the ones from the carbonyl as well, I've got lone pairs on highly electronegative elements, and I've also got lone pairs that are building up such that a sulfur is negatively charged. If I had to guess, I would say that this sulfur in particular is the nucleophilic site. So I'm actually going to label that as my nuke, the specific atom that I'm dealing with. So let's call this a nuke site, and that means this whole molecule is the nucleophile. That's the role the whole molecule will play. If that's true, then this other compound must be the electrophile. It's always going to be the case in a SNAc reaction that you're going to have an electrophile that is a carbonyl, and specifically the carbon of the carbonyl. So I'll label that E+ for my electrophilic site. What's left for me to do is to identify a leaving group. So I'm going to figure that out by noticing that the leaving group will always be attached to the electrophilic site. It has to be. because in order for this reaction to work as a substitution, I'm going to make a new bond from the nucleophile to the electrophilic site, and I'm going to have to break a bond in order not to go over the octet rule. So if I know that the carbonyl carbon is my electrophilic site, I've got two choices. I've got a chlorine or an isopropyl group as a leaving group. Another way of saying that is either I'm going to generate Cl- when something leaves, or I'm going to generate carbon- when something leaves. Which of those sounds better to you? Probably the chlorine. We're used to thinking about chlorine as being negatively charged, not so much with most carbon atoms. So it's worth guessing that the chlorine here will be my leaving group. In the language of our general example, we could call the chlorine the Y group, for instance. I know you're probably starting to see a pattern where the leaving group is always on the right-hand side of the carbonyl. That's not the pattern. Okay, that's just how I typically draw things, but it will not always be true. So make sure that you can do this from structure, not pattern recognition in terms of how I format structures. What's left for us to do then is to predict the structures of products, for instance. We're not going to talk over too much yet about whether this reaction is favorable or not. For now, we'll just focus on the fact that it's reversible, choose our arrows accordingly. If I know the general form, then what's left for me to do is remove the chlorine and attach the sulfur where the chlorine was. Everything else on the carbonyl will stay the same. So I know that I've got this isopropyl group here, and I've got the carbonyl, and my new bond I'm going to show in red, nice and dark since my red pen is dying, and that's going to be where the sulfur is attached. Everything attached to the sulfur is still there, so basically the methyl group is following the sulfur around. It's a little bit like getting pulled by a large dog down the street. And the sulfur is going to have just 2 lone pairs now, not 3. We're going to use the excess electron density on sulfur to form a new bond. Finally, we know that there's another product, and that's the leaving group having come off, having gained a lone pair. So we'll say Cl-. Okay, so this would be the example of a SNAc reaction, a specific one, involving an acid chloride electrophile and a sulfur nucleophile. Let's look at another problem. So I'm going to actually clean this part up so you still have the general SNAc picture. So we could choose maybe, how about like an ester? Something like that. And how about we use NH2-. What I'd like for you to do is actually assign roles to the reactant structure. So that means you need to find the nucleophilic site, the individual atom that you think is most likely to be able to donate electrons into a new bond. You need to find the electrophilic site for the SNAc reaction, and then finally you need to identify the leaving group. So pause your video and find those 3 roles now. Let's check your work. We know that for a nucleophilic site, we're looking for a place with unstabilized electron density, ideally a site that's also relatively sterically unhindered. If I look at all of the atoms in all of my reactants, I notice a few places that seem to be candidates. The oxygen, the other oxygen of my ester, or the nitrogen. All 3 of these atoms have lone pairs, which tend not to be as stable as electrons in bonds. But of all of those options, N- seems to be the place where the electrons are least stabilized. We have a buildup of electron density here on nitrogen, and moreover, nitrogen is not as electronegative as oxygen. So we really don't even have good properties for the atom that we're actually residing on. That means that the nitrogen here is likely going to be my nucleophilic site. And I think that if I know this is a SNAc reaction, for instance, because it's in Unit 5, I'm looking for carbonyls as electrophilic centers. In particular, this carbonyl here. So we've got our electrophilic site. There's a reason I chose to look for the electrophilic site first. That simplifies looking for the leaving group. Now I've only got 2 choices, either the benzene ring or this ethoxy group. Again, I'm going to choose those 2 on the basis of where I think I'm more likely to put electrons. So I can either have an O- if I put an extra pair of electrons on the oxygen, or a carbon- again with the benzene ring. That's probably not going to work so well. So I'm going to choose this whole piece here as my leaving group. It's not just the oxygen, right? This bond is what's going to break. So even though we're focusing on analyzing the oxygen, we know everything else attached to that oxygen is going to stay attached to that oxygen. So at this point, I've diagrammed all of my different kinds of roles in the reaction, and what's left to do is to make predictions about structural change given the roles. So I know my electrophilic site is going to connect to my nucleophilic site. Everything attached to the nucleophilic site is going to stay in the product. So my nitrogen will still have its hydrogens. I'm going to draw the new nitrogen carbon bond in red. And my carbonyl will still be present. And so will the benzene ring. All right, so that's one of the two products. The other is where the leaving group ends up. So I know that this oxygen is going to come off, and I know that the ethyl group attached to the oxygen is going to stay attached to that oxygen. So my leaving group structure after the reaction will be O-, looks like that. All right, so we've seen a couple of examples here of SNAc reactions, and in particular, we've focused on how to predict the structures of the products of the SNAc reaction by identifying these roles. So to be clear, using this analysis of structure to identify reactive sites is something that we'll use for the rest of the semester. So this is a good opportunity to make sure that you can use those skills. We'll talk more about them in more detail throughout this unit, and you'll see their use in other videos as well in subsequent units. So in the next video, we'll be looking at the mechanism of a SNAc reaction. So far, we've just been able to predict what the products will be. We've talked a little bit about bonds breaking and bonds forming here because we needed that to predict product structures, but we really want to get into like what steps are involved, what arrows should we push to show where electrons are going, are there any intermediates? All of those questions are still outstanding